on the behalf of the organizing committee, invite Professor S.S. PRABHU in the webinar series, 6th webinar series. So let me first introduce about Professor S.S. PRABHU. Professor S.S. PRABHU obtained his PhD in physics from the Tata Institute of Fundamental Research, India. Currently, he is a professor of physics in TIFR, India. He has published more than 70 research papers in reputed international journals and several articles which are popular and technical papers and in many magazines, and more than 80 plus research papers in conferences he has presented. And he has given several invited talks all over world in different platforms, conferences. His research interest includes ultra-fast time-resolved phenomena in materials, terahertz spectroscopy of materials, metamaterials, high field terahertz, and near field terahertz microscopy. This is the very, very important and highly rich, you see, the biosketch, the academic introduction about the Professor S.S. PRABHU. So I invite Professor S.S. PRABHU, please start the webinar, 6th webinar series.
So I'm from Tata Institute of Fundamental Research, as Sir has already introduced me, and it's very kind of you to be in front of all of you audience, and it will be a great thing for me to share some of the excitement that we do on our everyday life. So my research interests are in ultra-fast time-resolved phenomenon materials, terahertz spectroscopy, metamaterials, high-field terahertz, and near-field terahertz microscopy. So I am from the Tata Institute of Fundamental Research, which was formed by Professor Bhabha. He was supported generously by Tata, our the very well-known businessman of India. And we are located in Mumbai, which is I'm showing you on the map in the southern part of India, in Mumbai, and also we are right next to the sea, Arabian Sea, just like you have next to the Thiruvananthapuram. And this is the Peletron building, and this is the TIFR where we have our laboratory. So I will talk about this terahertz. So why terahertz? Because it can pass through many non-metallic materials, clothes, papers, plastics, etc. You can do imaging of this to find out hidden metal parts. So here you can see a man carrying a weapon hiding inside the this newspaper. And here is the scanning of Mahatma Gandhi's emblem or photograph, emblem or watermark as we call it, which is put on the note. And this you can very clearly see in the terahertz image. So this is the first such terahertz image of Mahatma Gandhiji has been done. And this is also of interest to military and other people because a lot of these RDX, HMX, TNT, NT, all these explosives have very specific type of what I call the frequencies, very specific modes which are present in, so which are very unique to those molecules. So you can call it like a frequency fingerprinting, just like we have a human fingerprinting. In today's talk, because of limited time, what I will do is I will basically speak about there are many things that we do in our laboratory, and those who are interested can look at our website. I have previously talked about in many seminars about our development about the terahertz source for CW as well as pulse sources and basically pulse photoconducting antennas, gallium nitride based antennas, etc. And we also design different terahertz optical elements like polarizers, filter, lenses, mirrors, and metamaterials. So out of these, I will speak mainly about the terahertz study of various materials which may be of interest using the terahertz spectroscopy. And I'll also speak about some of these metamaterials, which are the artificial materials. I will also talk about the study of materials using near field scanning terahertz microscope, the only of its kind in the country, and there are very few in the world. So which we have built in TIFR, and of course I won't talk about the designs or anything of these microchips or waveguide or fiber designs, etc. We also work on these Terahertz whispering gallery modes, and also we are working on the development of analysis algorithms of the Terahertz data. In future, we would like to start study of materials under high Terahertz field and study of materials under magnetic field. So in today's talk, I will basically give you some of the flavors of this study of material using near field scanning Terahertz microscope, which may be a very unique thing for you. We have several setups in our laboratory, which are all home built. None of these are commercially bought. These are all home built. We have Terahertz time domain spectroscopy, which gives you resolution of 4 to 7 gigahertz. Terahertz continuous wave spectroscopy, which gives a resolution of 2 to 4 megahertz. So you can see it is 1,000 times more than the time domain spectroscopy. And then we have optical pump, optical probe, time resolved reflectivity, or optical pump Terahertz probe, time resolved transmission, and near field scanning Terahertz. So there are multiple of these setups, and some of these setups they look like this. So those of you who are familiar with the femtosecond pulse oscillators will know that we split the pulses in two parts, and one part goes through a delay stage, which is delay line 1, and then it hits the PC antenna, it generates terahertz, then it passes through the sample, which is shown in green color here, and then it is detected here in this form. And if you put a delay line number 2, then you can also use that as a pump. So now you have a pump and a probe of the terahertz, that type of work. And one can do similar thing with, instead of terahertz probe, one can use optical probe. So in today's talk, what I will do is I will talk about the different materials that we have studied, and these are using different technologies, but mainly what I will talk about will be the Terahertz time domain spectroscopy of these materials. We have also developed this Terahertz continuous wave CW spectroscopy. This is a little bit of a different idea, where you have two lasers which are CW lasers, and they are slightly tuned with respect to each other. So like this is 800 nanometer, then this is 799 nanometer or 801 nanometer. And then when you mix it in a particular transmitter, and the same thing can be used as a receiver, you will basically generate a sine of omega t here and sine of omega 2t here. So these are mixed together. So basically they multiply, and you can have omega 1 plus omega 2 and omega 1 minus omega 2 terms. So out of which omega 1 plus omega 2 term is this slowly varying envelope, and that is basically the terahertz. And using this, you can actually do from 50 gigahertz to 1220 gigahertz. That is 1.22 terahertz, very, very high resolution spectroscopy. So these type of things, we use it for very specific purposes like whispering gallery mode and all those things. But I will, in today's talk, I'm not going to talk about it. But those of you who are interested in doing very high resolution spectroscopy, you can always talk to us, and we will be able to help. So in today's talk that I will describe will be the single crystal ND-GaO3 100 and 111 type single crystals of beta Ga2O3, which is Fe dope, then vanadium dope. And if time permits, a little bit of microcrystalline, this TAC selenium. And then I will talk about metamaterials, and then we will describe to you about how NSTM is done. Now, if you look at these natural materials, which are having, terahertz birefringence and dichroism, so we actually find that 100 and 111 substrates or crystals of ND-GaO3, they do show birefringence and dichroism. So this is a very popular material which is used in the terahertz spectroscopy to study basically the the superconducting thin films which are grown on these, or metallic films are grown on these. And metals or superconductors will completely block terahertz. They basically reflect terahertz. So as a result, you have to have a very thin layer of these, and then only and these layers are so thin that like few nanometers thin. So therefore, terahertz can actually pass through these layers, and in the transmission mode, then one can study. But if you want to look at the properties of terahertz birefringence and all that from the films, first of all, your substrate should not have any of these properties. So what we found out that is 100 and 111 NDJO3 does have this type of properties. So if you put this at 0 degree or 90 degree, if you rotate, you can actually see that there is a difference in the pulse. And then same thing also happens for 111 Brom crystals. And this is something that we see and from this. There are this is a terahertz pulse which is recorded in picoseconds by using the technique which I showed you in our setup. Now we have to take a numerical Fourier transform of this, because from time domain we go to the frequency domain. So in the frequency domain, when you go, you will basically find that with certain kind of analysis that we can actually get the refractive index, the real part, and also the imaginary part. So here is the real part of the refractive index of NDJO3, and you can see that there is a clear-cut difference between two orientation of the refractive index. So there is a difference in the refractive index. That means the materials are showing you birefringence. And if you look at the absorption coefficient, which is also related to the imaginary part of the refractive index, that also shows quite a bit of a difference. So this shows that the material is also having dichroism kind of property, and it definitely has shown this in two different orientations. Now, these natural materials, among them, the very popular material which is coming up now is gallium oxide, which is beta dope. Beta type GO203, which is Fe doped. We also doped it with vanadium, and we also had an undoped GO203. This was grown by Professor Tamil. He's one of the leading experts in the world grows crystals. And then Professor Arnab Bhattacharya, who is also a very well-known semiconductor growth person. He's now currently director of Homi Bhabha Center for Science Education. So this is done by their student, joint student, Manisha. She's actually from Kerala. And she grew this GO203 and she doped it with Fe. What happens is this Fe goes as a very deep acceptor level inside, and as a result, it takes away all these carriers and makes it this devoid of carriers. So basically, it becomes semi-insulating kind of. So if you look at Fe doped GO203 in two different orientations, you can very now clearly see that I will just make here. Okay, arrow only. So you can very clearly see that there is a clear-cut difference between these two orientations, and spectra is not much different. There is a little bit of a change in here, but you can basically see that this Fe dope thing has actually shown quite a bit of birefringence. Now, Manisha has basically developed this, GO203 crystal growth parameters. So what they have is a optical furnace. So there are two mirrors inside that, and it actually they focus in the center, and that is where you put the material and it melts, and then they slowly pull it on both sides, and then it becomes, it grows as a nice crystal. So this she also used vanadium to dope it. Now vanadium is a very peculiar thing, but GO203 has many of these advantages over other semiconductors. First of all, it has a big band gap. It has very high breakdown field, so one can have devices made out of these which can withstand very high fields. And if you just look at the undoped gallium oxide, it's very transparent, colorless, and a very wide bandgap semiconductor. So Manisha grows these by optical float zone technique, which I explained to you before. And this has a base center monoclinic structure with C2M space group symmetry. So I'll explain to you what that is. So she grew this crystal. So you can see this is a vanadium doped crystal, and this is an undoped one. And see how beautiful these crystals are. And these are the X-rays. So those of you who are familiar with X-rays will know what this means. The peculiarity of this crystal is that if you have A and B axis, the C axis actually is not really exactly perpendicular. It is 13.7 degree off from the main axis. So the result, since it is on the other side, so total angle becomes 103.7 degree. And this is happening is because if you look at this gallium oxide from the top or from one of the directions, you will find that from the top it looks like very symmetric. Hello, are there any questions? Yeah, so along A, if you see, you will see that it is looking like a very properly symmetric thing. But while if you see it from the B side, you will realize that there is a certain gallium oxide chains which are going like a spiral, and this actually gives it an anisotropic thing. Basically, it is not the same in all directions, and as a result, it will start showing you different. So the light which is passing through along A or which is passing through along B, it would actually encounter two different types of crystals, and as a result you see this kind of variation. Now there were a lot of other measurements which were done on this. So for example, photoluminescence emission spectrum was checked, and when you have this undoped crystal, the luminescence was pretty nice. However, when it was doped with vanadium, it actually completely removed the luminescence. Almost luminescence was zero. And this happens because transition metal dopants, which is like vanadium, they are known to give rise to very deep level states. And these deep states actually act as a very efficient non-radiative recombination for these emitted photons, or basically the electron and hole pairs, they get trapped in that without getting any emission done. So as a result, you don't see any kind of luminescence. And they also remove these carriers, and as a result, the sample also becomes semi-insulating. So what happens is, if you just do a transmission study of these doped vanadium doped gallium oxide, you will find that over a large range of wavelengths or light, you will see that it shows a very steady change, and there are really no sort of absorption bands or anything. However, for a gallium oxide, what happens is, because there is these carriers are not compensated, there are certain plasma frequencies which are created because of the presence of these carriers, and as a result, for longer wavelengths, there is a absorption band. So if you look at these data, you will find that at 10K and 300K, the luminescence is pretty nice from gallium oxide. However, it is completely quenched for V-doped samples. You can see that as a yellow line here. And this is the transmission that I was talking about, that if you look at the transmission part, it is quite flat for a V-doped sample. However, because of the presence of these carriers, it has basically a sort of a plasma, we call it actually the plasma portion of this. And one can actually figure out how much is the carrier concentration. Now, I mean, these are all what I actually talked about. The most important part here is I want you to observe this in the transmission. There's two orientation, 0 degree and 90 degree. They do show quite a bit of change in the transmission. So this actually is the reason, basically is called birefringence. And for studying that, at terahertz range, we use what is known as the terahertz spectroscopy. So this is our typical terahertz spectroscopy setup. We have this 10 femtosecond 80 megahertz pulse laser, red laser. So it is split into two parts. So one part actually hits this photoconducting antenna. It generates terahertz, and this terahertz is collected by these two parabolic mirror. It is focused on the sample, then it is passed through other two parabolic mirrors, and then through ITO plate it is focused on zinc telluride. The second pulse comes through this delay stage, and that is also transmitted with this over zinc telluride. And what happens is, because of the presence of this terahertz field, zinc telluride is a birefringent electro-optic crystal. So what it does is, it actually, because of the presence of this electric field, it makes it little bit of birefringence, and as a result, the two beam, the red beam actually develops a kind of elliptical polarization, which we use this with Wollaston prism and quarter wave plate to split it into two diodes and then measure how much is the change in the. So now we will say about little bit about this anisotropy in gallium oxide crystal. So as I mentioned, the gallium oxide chains along aligned along B axis gives rise to this anisotropy, and terahertz radiation can actually distinguish this very well. And what we found out was, we had one of the largest refractive index difference between the two, and you can see that the pulses are pretty well separated in this case for both these orientations, 0 degree and 90 degree. However, spectrum shows absolutely no change. It is almost the same. So this is basically a very beautiful crystal which shows without any additional modes, just a change in the refractive index. So we calculated the real part N and imaginary part K of the refractive index, and it shows a very clear-cut birefringence. However, it is not showing any dichroism, unlike in Fe doped thing. So this K remains almost the same. And for various different thicknesses of G0203, you can see that as the thickness is very small, 300-400 micron, then you will have very specific mode at which it shows this refractive index, the polarization change. And as the thickness goes on increasing, then various other modes keep coming. So how does one quantify all this? I mean, so far so good. Okay, we made this observation. So one has to quantify this. So for that, you have to know what is known as an orientation ellipse. So we have this ellipse which is given by this equation. So if you look at this ellipse, so this is S of phi, and this is the electric field. Now it has two axes, A and B. So if A and B are equal, then this is actually a circle, and then you have what is known as a circular kind of polarization. If and the other part is, if the delta basically, which is the phase difference between the two, that is exactly equal to pi by 2 or something, then you will basically have either the linear polarization or circular polarization. And if B and A are not equal, then you have what is known as an elliptical polarization. So just using this ellipse, orientation ellipse, one can actually look at these parts. So here, those of you who are not familiar with these polar plots, so these two lobes means there is only one cycle. So basically, if you rotate the crystal, you will have one maxima, then minima, then again one maximum, and then you are back to original position. However, if you have a quarter wave plate or that type of thing, then you will see, instead of 2, you will see 4 lobes like that. So in our polarimetry setup, what we had was this electric field of the terahertz was made linear, vertical oriented. So this is the V doped G0203 crystal, and so the incident field is E naught, and when it passes through this transmission, this A and B e raised to I delta, this is what is the change that would be incorporated in the transmitted field. This transmitted field is passed through polarizer. and this is the equation which is a polarizer tilted at an angle phi. So this is the matrix. This is how it will change the transmitted field, and this transmitted field is further analyzed by the analyzer. And then EA will be given by 1001. So we are looking at one of those components, either vertical or horizontal, depending on this field. Now, when you solve all these, you collect the data for every angle of this sample, different polarizer and entire analyzer thing. Then you can fit this, and you will see that at these particular points, the A upon basically B is so small that this is actually blowing up, and here B is very small, large, but A is small, so therefore this is going into the minimum. So you basically have the different polarizations of this, and you can also look at the different phases of retardation on this side. So these are the different ellipses that you can see, and these are done at some different frequencies. And I will explain to you why these frequencies were chosen. They automatically came from different analysis. And so these are the two-dimensional plots that we have plotted here. And you can see that the co and cross polarization parameters, they actually show complementary pattern. So here, if you have a co-polarization minimum, then you have a cross polarization which is a maximum, and then vice versa. And at these 2 points, this is where the thing will behave like a half wave plate. However, near the edges of these, it will behave like a quarter wave plate. Now, this is known from the phase, and you will say, all right, but this is not the right way to, this is not the only way to show this. So therefore, we have to go towards what is known as the Stokes parameter calculation. So that requires you to know the ellipticity and the orientation angle for this. And this is calculated using the Stokes parameter. So these are the equations for the Stokes parameter in terms of A, B, and delta. And then you can calculate chi and psi from this. That is basically the ellipticity and the orientation angle. And if you plot this, now you will very clearly see at 0.38, 1.0, 1.7, and 2.28, very clearly these 4 lobes. That is where this crystal will behave like a quarter wave plate of the terahertz. And at these 2 specific frequencies, it will behave more like a half wave plate. And this very clearly tells us how we can actually completely characterize the gallium oxide or any other crystal using this polarimetry. Now, we did also similar work many years back with selenium. And there also it was done in collaboration with Professor Pushan Ayub, one of the very eminent crystal grower and material scientist. He has retired now. So there we use these trigonal form of selenium, and we could actually also see the same kind of behavior. Now we come to from natural materials to now artificial materials, which are called metamaterials. So sometimes people call these as meta surfaces also. Both are fine depending on whom you are talking to. So for these, we actually work with Professor Achenda Venugopal and Professor Siddharth Dattagupta. Professor Venugopal now is a director of NPL Delhi. And Professor Siddharth Dattagupta is in IIT Mumbai, Electronics and Electrical Engineering Department. So here what we did was we basically made these type of periodic pattern. So you can see if I don't have these 2 bars, but I only have 1 bar, then what happens is this is the periodic bar. So this period is there everywhere. Now, when you do a transmission of terahertz through this bar will actually get excited, and as a result, you will see an absorption, 1 dip in this spectra. However, if you introduce these additional 2 bars, now what happens is it actually generates this quadrupole kind of interaction, which destroys this dipole. And as a result, now this frequency which was blocked here would now start passing through. And this is called basically electromagnetically induced transparency. Basically, because you have opened up a window of this transmission frequency in this region. So we have done several other work like hollow T-shaped metamaterial or Terahertz filter, then cut wire metamaterials, Terahertz band polarizers, etc. So many of these works we have done. So this is a simulated and measured ones which match pretty well. And here, this is a cut wire metamaterial which shows certain bands it is acting like a complete polarizer, and certain bands it is just passing through as this. Now with my postdoc now he's a professor at Tata University, we wanted to do this polarization control dual resonant Terahertz transmission through these regular aperture arrays, because we wanted to study these different Q factors for the polarization state, etc. So the idea is that you have a slit, which is of course a periodic slits. This will be set from all directions. Now, if you have a polarization of light which is horizontal to this would actually pass through. However, a vertical one would get excited, will excite a mode, and then that part will not pass through. So as a result, you will see that for a particular orientation of the terahertz, there will be a resonant transmission, while the second one will not transmit anything. So you can see the simulated and the experimentally measured spectra, and they match pretty well. And this is for the rectangular array of these materials. Now we made several such different arrays, and then I am just showing you here 3 of those, and you can see the experimentally measured and the actually simulated one. The dotted ones are simulated ones, and the continuous lines are the experimentally measured ones. And you can see that they match pretty well the simulated predictions. Now, these are the actual rectangles that we made with their specific dimensions. And now, if you look at these simulated parts, you will see that there are several such modes which come up in these materials. And you will see that these are all, of course, numerically calculated. So you have, specific softwares like COMSOL or CST microwave or many other Sintra or many, what is that? There is one more popular one, numerical and all that. So they all actually are capable of giving you these type of modes. So this is of course done using COMSOL, which we typically use. And you will see that these are all theoretically simulated ones. Now, the idea was we wanted to measure them in practice. So this is my student, Ajinku Punjal. So he basically, we built this near field scanning terahertz microscope. And the idea again is very simple. I mean, you have the laser, you split it into 2 parts. So one part goes through delay stage, you generate terahertz, pass it through and focus on the sample, while the other part goes and actually puts, so this is where the probe tip of the terahertz we are putting. So this is where the terahertz field is sensed, which is in the near field, that is right next to the sample. So this is different than the other terahertz setup. So in the other terahertz setup, we would measure it far away with using another set of 2 parabolic mirrors. So the terahertz field which will be measured will be very far away. So that's why it was a far field measurement. While here we are just measuring terahertz as it just coming out of the sample or whatever pattern. So basically what you will do is you will basically measure the time pulse of the signal, then you will take a Fourier transform and you will get an amplitude and a phase of this. So the sample can be moved along X or along Y, and the tip remains stationary. And then you can have for for every position here, this kind of a map as a function of time. So this entire pulse is measured at one particular point. So like this, for every point on X and along Y, you can generate this kind of matrix and this kind of maps, as they call it. And then you can also take a Fourier transform of that. So you will have then amplitude and phase maps. Now, based on this, there are the vectorial mapping of these near fields that you can do. So this is how the tip is, and now you can see that there is a small gap here. So what happens is, when you put the red light in between, it will generate carriers, and whenever the Terahertz field is in this horizontal direction, it will basically you will see along Y direction, then it will basically excite this, and you can measure. So this will measure the Y component of the Terahertz field. While if you just turn it exactly perpendicular, then you will start measuring the X field of this. Then if your tip has this vertical kind of a gap, then you will actually measure the field along Z. So you can measure X, Y, and Z, all three components of the electric field for a given sample. So this way you can completely measure this field. So this is the tip here, and this is the setup we have in TIFR. So this is the delay stage. This is where you generate terahertz. It comes here and gets focused here in this portion, and this is the enlarged portion here. So it gets focused right next to the tip, and we have this another red light which is directly coming and hitting the tip position here. Basically this gap position here. So this is where we have to put the red light, and then basically you scan the sample up and down, and then basically for every position of the sample XY, you measure the time delay and record the pulse. Now once you do that, you will basically get the time evolution. So now here actually we have a rectangular slit which is of course part of the periodic thing, which is here, and now I will show you how the time evolution takes place. So right now there is no signal, and now the pulse will start coming, and as soon as it starts coming, you can see it is coming through this rectangular portion, and this is the pre-pulse and this is the main pulse. So now the main pulse has come out with different modes. So you have dipole, quadrupole, and all those different modes. As a function of time, you can see, you can monitor them, and so this is the pulse which is recorded at each and every pixel point. But when you put together, you can generate this kind of a map. So this is called the time evolution map. This is like a film, of the evolution. But remember, this film is basically having, in principle, billions of frames per second kind of thing. So it takes certain time. Now, once the pulse is gone, then you will see that there is no more here. Now you can also look at what are the frequencies which are coming out. So this is the frequency evolution, and this will give you another different information. So in the center you have this same square, and now watch what happens. So this is the main mode which has come out of this, and now this is the single mode, and now you will have dipole and quadrupole, and see these are different modes of this frequency which keep coming out of this, and then you can very clearly see different modes coming out of this periodic structure. So you can see now very nice dumbbell shaped thing, and now the signal is gone, all the frequencies are gone, and now for higher and higher frequencies there is nothing here. So this is how you can actually look at the time evolution and a frequency evolution of this. So we have done this simulation and experimental thing. So this is a polarization dependent transmission. So you can see simulation and experiment, they match pretty well. And yeah, so this is how one can do near field mapping. And now I come towards the the last part where Ajinkya, I mean the same student, we were making different, see, we design different types of metamaterials which are having different properties. So we were actually trying to make a filter for the transmission of certain frequencies. So according to some physics, some diagrams we design. So he said, there is this AI ML. So I said, I know AI ML, and he had tried many years back, but that student was not successful. So I told him, we have this machine. So can you do? Can you make the machine learn that this is the shape, then this is what is the spectrum, and like that? So then he said yes, and then he basically taught that machine with some 20,000 different designs and how the spectra looks. And then I told him, using the AI, now I will give you the curve, let the machine give us the design. And then he used that AI algorithm on the machine, and then we gave this spectra, and the machine actually gave us back this design. And when we fabricated it on this Captain, and you can see that this is the simulated data and this is the actual measured. The black one is the experimental data, and the blue one is one with our simulation, and you can see it is matching pretty well. This much of change or a drift is acceptable because of the material parameters can be slightly different. It is very sensitive to that. So this way it was done. So to sum up, basically what we have done is our research basically is for the near. I mean, right now we are doing near field scanning terahertz microscope. So if you are interested in your surfaces, metamaterials, we are always welcome. This actually gives you a very different information which is not possible. There are very few places in the world where you can do this. In India, ours is the only place where you can do this. We also make these waveguides, fiber designs, etc. for detection of molecules. We also work on these terahertz whispering gallery modes for detection of very sensitive things. I have not talked about that. Any of these development analysis algorithms we have worked on. And we continue to work on these new terahertz crystals for the generation and detection. So this is also quite an open field. And we are currently doing optical pump terahertz probe studies of different materials. So hopefully next time I will have a lot of those time resolved phenomena. And we will eventually get into the materials under high terahertz field and under magnetic field. And eventually we may want to develop on the terahertz nanoscopy using STL. So I have to acknowledge all my former professor, Vindulekar, retired, now settled in US, and Professor Gopal, who is now director at NPL. And these are all the past students, and currently Dhanashri, Ajinkya, and Yamuna are working. So out of this, Ajinkya's work I showed, and funding is from DAE, and we have assistance from Gajendra Mule, and there are many of these collaborators. These are Professor Rana from ISER Bhopal for materials, Professor Gagan Kumar for different metamaterials, optical metamaterials, Professor Rajiv Kumar for our protein related chemistry work, Professor Ranjan Singh for different metamaterials of different type, and Professor Divakar Rai Chaudhary also for metamaterials of different types. So I mean, basically I learned a lot of things from these people. So I would give credit to all these students, past students, and these are current students. She is my current postdoc, Dr. Shraddha Chaudhary, and this is Dhanashri, and this is Ajinkya. So I would give credit to all of them. So thank you very much. And this is, if you have any collaborative things, you are always welcome to write to me. This is my email. And yeah, so thank you so much. And if you have any comments, questions, please let me know.